Hello students, I am Dr. Tanmoy Vishwas. I hope you all are fine. So today we are going to discuss about an interesting topic, that is aromatic electrophilic substitution, specifically about 5-member ring system, 5-member heterocyclic ring system. I know this topic sometimes seems to be difficult for students, and that is the main reason to make a dedicated lecture on this topic. Okay, so today we are going to discuss mainly the furan, means this X equal to oxygen, then it's furan, sulfur means thiophene, and NH means pyrrole. And in presence of electrophile, the aromatic electrophilic substitution occurs and produce three type possibilities there, three type of product formation. This product is considered as C2 substitution, this is considered as C3 substitution, and this is specific for pyrrole, and this is named as N1 substitution. Okay, so mainly we will focus on this C2 and C3, and we will discuss which one will be the product first of all and why, with complete mechanism, and finally how the selectivity for C2 or C3 or C3 or C2 this could be tuned, and finally disadvantage and advantage of this heterocyclic compound, which are actually pi excess nucleus. The term means, in this case if you look at closely, this heteroatom has a lone pair, and if for this case 6 pi electrons are distributed over 5 atoms. Okay, that's why they called pi excess nucleus, means with respect to each atom there is more than one electron, and that is the reason for them to be considered pi excess nucleus. And this pi excess nucleus makes them very reactive for AES, means aromatic electrophilic substitution, because they are electron rich, so they are ready to give their electron to the electrophile, which is actually an electron deficient species. So lots of chemistry to be learned in this video. I request you student, please watch the video until the end with a cool mind, and don't be hesitated or confused or in a mental trouble, because these things are the obstacle for understanding chemistry. Okay, so let's start. So now the question is that in this case, before going to details, we need to remember few points. What are those points? First of all, the resonance energy, because since it is aromatic electrophilic substitution, so aromaticity is involved in this process. So for that purpose, we need to understand the resonance energy, better to say aromatic stabilization. So in this case, we are mainly focusing on aromatic stabilization energy. Okay, generally we consider that a molecule, if it is more stabilized, that is less reactive, but this is a general statement. Some other factors are also responsible. Okay, we will learn slowly. So first of all, the resonance energy of furan is around 17 kilocalorie, the resonance energy of this pyrrole is around 21 kilocalorie, whereas the resonance energy of thiophene is 29. So from this discussion we can understand that thiophene is the most stable among these three, and consequently this is generally least reactive. In case of pyrrole and furan, there is some confusion. Why? Because you can see there is one hydrogen, okay, and that hydrogen could be deprotonated in presence of base, and if it's possible, then it will generate an anion which is more electron rich and more active for AES. And that's why I told that generally, because of this methodology, you can say that base induced control on AES is possible on pyrrole. What do I mean by the statement? That normal pyrrole you may get a particular substitution, maybe in presence of base you may get further substitution, for example di substitution. In future I shall upload some dedicated videos on this, so I shall provide the link, please visit for better understanding. So from this statement we understood that although they are pi excess, but still they have some difference in reactivity because of point number 1, aromatic stabilization, and point number 2, this presence of heteroatom. Okay, let's go to the mechanism part. See, mechanism, actually this is mainly we are discussing about, this is general but mainly focused on furan and thiophene. Okay, So what do I mean? In this case, this X is equal to either oxygen or sulfur. So just C2 substitution means this is actually a C2 position. So C2 substitution at this means, so this position substitution. So how it happens? First electrophile attacks, and you may consider that it will give this electron to electrophile. So it will result in this. And how this is stabilized? First of all, this double bond could be shifted here and positive charge will come here, one canonical form. Another, see, this heteroatom has lone pair, so it can push and it can result another canonical form. So in this case, 3 canonical forms possible. Let's see about the C3 substitution. So how C3 occurs? This bond attacks the electrophile and it produces this, and here the positive charge. Now this lone pair can participate in stabilizing this. So in this case, what you observe, 2 canonical form possible. Now in case of C3 attack, 3 canonical form means more canonical form. So we may conclude that C3 attack is associated with lesser energy of activation, as the intermediate is stabilized more through resonance. Okay, and if the intermediate is stabilized, its energy is less, then energy of activation is less, rate of reaction is higher. So this is a general statement. Majority of cases this is followed, that aromatic electrophilic substitution on 5-member heterocyclic compounds, mainly they prefer to have C2 substitution. Some exceptions are there which we will discuss later on. Okay, but as I told sometime before, for pyrrole, some reactivity, specific reactivity possible for this NH. See, this C2 substitution or C3 substitution follows similar trends like the thiophene and furan, which I have discussed in the previous slide. So now let's focus a little bit on this N1 substitution. Okay, so by the way, generally this thing is mainly dependent on base. So you may consider this is a base induced reactivity. Okay, and another thing, for harder electrophile, this thing is preferred. One of the example, let me give you. If you take this pyrrole and if you take base like sodium hydride and methyl iodide in anhydrous solvent like ether, so what happens? From that thing we get N-methyl pyrrole. Okay, but instead of that, if you take a base like Grignard reagent and another electrophile, the carbon based electrophile, then it is preferred on this C2. Okay, so this is the exceptional example, that's why I am telling that this is because this methyl is a good electrophile, heart center, iodide is a good leaving group, and nitrogen is a harder nucleophile. That's why this reaction happens here. Okay, so that's a special example. Okay, just keep it in mind. Now let's go details about some examples. Acylation. Okay, by the way, why we are directly going to acylation? Generally we may think that why we are not going for alkylation. What do I mean? For example, if you take furan and take something and produce this methyl furan, 2-methyl furan, we know that AES is preferred at C2 position. Is it possible? For example, if we take methyl iodide as a alkylating agent, okay, this is not a good choice. Why? First of all, these are pi excess nucleus, and actually better to say they are electron rich system, and we know that Friedel-Crafts alkylation, the alkyl group has a plus I effect, for which it increases the electron density in the ring. So this is, you may consider that further active. So it is very difficult to control. Okay, so difficult to control selectivity. So that's why alkylation is not preferred. But if you think you need 2-methyl furan, how can you prepare? First of all, you can follow on bypass route, like you can take butyl lithium in anhydrous solvent, and what it will result? It will result this anion here, this is more acidic, okay, lithium. And another, after that, if you take methyl iodide, then selectively you will have this 2-methyl furan. So in this case you have to follow a different strategy because of this reason. Okay, so I guess you have understood this point. Now let's discuss about our main topic, examples. So see, acetic anhydride in presence of BF3, what it generates? It generates actually acylium CH3COO plus cation. This is actually electrophile, and as we told that this 5-member ring system are electron rich, so they undergo reaction and selectivity on the C2. Okay, so this is a C2 selective reaction. So in this case BF3 act as a Lewis acid. Fine. In case of pyrrole, if you take simple pyrrole and acetic anhydride and you provide little bit heat, it resulted in 2 substitution. I'll come about this again. In case of thiophene, if you take thiophene and this acetic anhydride and in presence of little about phosphoric acid, it resulted in similar substitution pattern. Now question is, why pyrrole don't need any Lewis acid? Why no Lewis acid needed for pyrrole? This is because pyrrole is highly electron rich and susceptible for AES, because the nitrogen atom, this atom is less electronegative, so it can delocalize its electron efficiently. Then you can argue, sir, why not sulfur? This is also less electron, but remember sulfur size is bigger, so that is a disadvantage. So whereas nitrogen can localize its electrons so much efficiently that this is possible. Second, another thing, this NH bond, this NH bond's polarity also plays an important role in activating pyrrole for AES. Okay, that is the reason it shows this much unique reactivity for aromatic electrolytic substitution. And proof of this statement, just look at the 4th example, this example. Pyrrole reaction with ammonium carbonate, aqueous. Generally we prefer to avoid aqueous system for this AES, and see under 130 degree centigrade seal tube, although it is relatively drastic condition, it produces this. By the way, what is seal tube? Seal tube is a setup. Actually it is a pressure withstanding setup, and I have used this in my lab. So this is, using this it is possible to do reaction under relatively drastic condition, and you can consider, as I told, it can hold pressure, so probability of blast of the reaction setup is less. Okay, and this ammonium carbonate is nothing but a combination of, you may consider, ammonia gas plus water plus carbon dioxide. Okay, and that's why, see, under 130 degrees centigrade all 3 are gas. So in order to keep the gas into the reaction medium safely, seal tube is needed. Additionally, in this case, this carbon dioxide acts as an electrophile, and we know that electrophilic substitution on pyrrole, simple pyrrole, prefer to have C2 substitution, so this ammonium salt is produced. By the way, one important information I want to share with you, that we are discussing simple pyrrole furan derivative, but if you take benzene ring fused, means such kind of this thing, means this is indole, benzofuran, benzothiophene, those cases aromatic electrolytic substitution prefers to have C3 position. I have discussed in this topic about a dedicated video on indole. So just as an exception, keep it in mind, for simple ring system it happens in the C2, whereas in case of fused with benzene it's C3. This is because lesser waste or lesser energy of activation, because the resonance is not involved in this benzene, means the aromatic stabilization of this benzene nucleus is not hampered in this case. Okay, this is the exception, keep it in mind. Fine. So as a conclusion, we can say that it is better not to try AES on this 5-member ring of AES of alkylation, because they are activated and alkylation activates this thing further, which I have discussed. So from this discussion, incomplete, first of all, what you have learned that C2 substitution preferred, and in case of pyrrole this is the most reactive, and finally if you fuse this 5-member ring with a benzene derivative, means for example indole, then the substitution prefers on the C3 position. substitution, better to say aromatic electrophilic, and in this case we preferred electron withdrawing or deactivating substrate because these derivatives, these products are already electron rich. So if we attach some electron deficient substrate, they are less reactive, so it is possible to have selectivity into the product. Fine. Okay, now let's discuss about nitration. See, for nitration we know that in every type of thing we use NO2 plus as the electrophile. Now the target is how we can use this electrophile under, or we can generate electrophile under milder condition. Okay, milder condition. Why I am telling this thing? Generally we use mixed acid, concentrated sulfuric acid, nitric acid. Is it good choice for this heterocycle? Obviously not, because we know that this concentrated sulfuric acid, nitric acid, they generate NO2 plus into the reaction medium which acts as electrophile. Fine, but they are strong acid, and another thing, they are oxidizing in nature. See, this 5-member heterocyclic compound means these are electron rich. They are electron rich. So if some substrate is electron excess or electron rich, it has a tendency to give electron to someone, and that is nothing but oxidation. So that's why oxidation is possible. Another thing, in presence of strong acid, there is a chance of polymerization, because heterocyclic compounds are not stable in acid, or some dimerization, trimerization, some reaction possible. So that's why it is not advisable to use acid directly instead of some smart reagent possible. For example, nitronium tetrafluoroborate. Not only this reagent have another unique property, that is this BF4 minus. This is actually non-nucleophilic, non-basic anion. Non-nucleophilic and non-basic anion. By the way, I have already discussed about non-nucleophilic bases, so please visit those lectures. That's an interesting topic I believe students should learn. So in this case, in ether, it undergo nitration, and as usual selectivity is C2. But for example, in case of pyrrole, see, we have used nitric acid, acetic anhydride, and we got this. Now question, why nitric acid? Because nitric acid and acetic anhydride produces the electrophile nitronium acetate. Okay, and in this case, this acetic anhydride is acting as a dehydrating agent. So it dehydrates the nitric acid to generate the nitronium cation, which is acting as the electrophile. Okay, fine. And in case of thiophene, see, nitric acid, acetic anhydride at 0 degree centigrade, it produces this. By the way, one point to be mentioned, see, for pyrrole minus 10 degree is enough, but for thiophene relatively higher temperature, that is 0 degree. So this is another proof that pyrrole is relatively more reactive than thiophene for this nitration reaction. Okay, fine. So this is about the nitration. Now let's go to discuss about the halogenation. Now halogenation, before going to halogenation, I request you please understand or keep one statement in mind, that halogens are orthopara directing but deactivating. I have uploaded a dedicated lecture on AES on substituted benzene. I request you please visit that lecture if you feel that statement is difficult for you to absorb. Okay, so let me discuss here little briefly about this topic. See, for example, just consider the benzene with Cl. Okay, so we know that Cl is a very high electron withdrawing, means electronegativity is higher, so consequently it's withdrawing. But see, this lone pair, Cl has lone pair, which is possible to delocalize here, or in this case ortho, or you may consider this. So because of this lone pair, they are orthopara directing, but because of the minus I effect, they are withdrawing and deactivating. Okay, so this is the interesting point I believe you should remember. Now another point, that in this case, just look at this example, that this furan react with bromine in dioxane at -5 degrees centigrade produces this 2-bromofuran, as usual selectivity at C2. Now question, what happened if we carry out this reaction room temperature? Generally it is always advisable to carry out any reaction at room temperature. What will happen? Actually halogenated product will obtain. Okay, why? Because these heterocyclic nucleus are so reactive. Additionally, see, if you look at the thing, what is the polyhalogenated? For example, if you consider thiophene, that is such kind of thing, okay, will be produced. Now look at little carefully that halogens are not only withdrawing, they are also oxidizing in nature. Okay, so halogens are oxidizing, means they have 7 electron into their outermost valence shell. They want to have another 1 electron desperately. Remember the word desperately. That's why they prefer to take electron from anyone else, like if situation you permit, then from heterocyclic. And in this case, previously there was a CH, just remember, and here CH is converted into CC. So this part you can consider as a oxidation. Okay, so in this way this is possible. Now let's come to the main topic. So we have understood about this -5 degrees centigrade reaction occurs. But if you do the furan, then -78. By the way, for bromination, what happens? Bromine molecule has one instant dipole. This is bromine plus, bromine minus, and actually this bromine plus is acting as a electrophile for this aromatic electrophilic substitution. Fine. In case of this NBS, it has a permanent dipole. What do I mean? If you look at the structure of the NBS, this is N-bromosuccinimide. Okay, so this is N-bromosuccinimide. Now this bromo is delta plus and nitrogen is delta minus because of electronegativity difference. Okay, so this bromine has a permanent polarity, so reaction is expected to be easier. Second point, pyrrole is more reactive for AES, that's why reaction is possible at -78 degree and similar selectivity is observed. Not only this, if you use SO2Cl2 in ether at 0 degree centigrade, it undergo chloro substitution. Generally direct chloro substitution is a difficult thing. Okay, so that's why this reaction is very advantageous. Fine. In case of thiophene, if we consider that, then this bromine ether, and along with that it need 48% HBr and -25 degree centigrade, it undergoes similar substitution. And in this case of iodine aqueous nitric acid at 90 degree centigrade, see this two substitution. By the way, nitric acid in this case is actually a oxidizing substance, means it withdraw electron from somewhere else, and iodine is a halogen but having a relatively less electronegativity, so it is easier to withdraw electron from iodine, and after withdrawing of electron from iodine, it generates electrophile, and which participates in this reaction, because like other halogens, chlorine, bromine, iodine is not that much strong electron deficient or electrophile, so nitric acid is responsible to increase its electrophilicity. Okay, so this is the chemistry behind choosing this reagent. Okay, fine. So let's discuss about the sulfonation. Okay, so now question is, as we told, it's pi excess nucleus, so it expected that sulfonation occurs well, and previously I have discussed it is advisable to avoid the use of direct acid. For that purpose, pyridine sulfur trioxide addact. So this is actually a addact between pyridine and sulfur trioxide. So pyridine is actually acting as a base and sulfur trioxide acting, so it's a Lewis acid base addact. Fine. So in presence of DCE, dichloroethane, room temperature 3 degrees in 3 days, it results in this pyridinium sulfonate of this corresponding furan at 2 position substitution, and after workup with acid, it resulted in 2 substituted acid. Similar thing is observed in case of pyrrole and in case of thiophene also. By the way, in case of thiophene, this barium hydroxide step is involved, because along with this monosulfonation, there's some disulfonation product, and that's why this barium salt is precipitated out as a crystal. So it is easier for separate the monosulfonic acid, that's why this additional step is employed. Okay, fine. So now let's discuss about C3 substitution. Just look at little carefully. previous all the discussion I told that these 5-member heterocycles are C2 substitute, means they preferred the C2 substitution for aromatic electrophilic substitution. Now question, why C3 and how this could be obtained? The chemistry need to be understood easily. Actually, what chemistry we are utilizing in this lecture is steric protection. Steric protection of C2. What do I mean? Just look at the molecule little carefully. And actually this is dedicated for pyrrole. Remember, only pyrrole this is possible. Okay. So just look at this molecule. First of all, it is a triisopropyl silyl amide derivative. Okay. And how this could be prepared? The corresponding anion of furan and triisopropyl silyl chloride, if you react, you will get this one. So what happens in this case? In this case, these two positions, this are not accessible because of the bulkness of this 3 and silicon. You may think that, sir, they are far apart. I have written in that way. Just remember, the size of silicon is more than nitrogen because it is another one row down. Okay, so it's a third row element, silicon. Additionally, this isopropyl group 3 very bulky. That's why electrophile cannot access this C2 position. Consequently, they are forced to access this C3. By the way, I have already discussed that pyrrole is very electron rich, very active. So it is not quite difficult for pyrrole to get C3 substitution. However, the condition needed for C3 substitution is relatively drastic compared to C2. Okay, so let's discuss little bit about this substitution. So first of all, if you take acetic anhydride and copper nitrate, better to say cupric nitrate at room temperature, acylation reaction happens. I think you may little confused that, sir, previously when you have used acetic anhydride plus nitric acid, HNO3, you have showed that it resulted in nitronium acetate NO2 plus ACO minus. But in this case, means actually in that reaction you have generated nitronium electrophile, but in this case you are showing that it is generating acetylation, means acetyl cation which is acting as electrophile. Why? See, that is because of this proton. Actually, because of this proton, acetic anhydride get broken into acetic acid, because along with that acetic acid is produced. Okay, but in this case no proton is there, it's an proton free environment. Consequently what happened? Nitronium cannot be generated, so only one option left, that is this acetyl cation generation. That's why this acetylation reaction occurs. I guess we have understood. But this is not the first step. After that, this protection is there, and how this protection could be broken? By the use of fluoride anion. See, in this case tetrabutyl ammonium fluoride. Why tetrabutyl ammonium? Because quaternary ammonium salts are soluble in both organic as well as aqueous medium. They are actually a phase transfer medium. So this fluoride attacks this silicon center and this open. First addition, then elimination. And what is the driving force? Because this silicon fluoride bond energy is pretty high, because back bonding means this 2 p pi d pi back bonding. Okay, so this is donated to the vacant d orbital of silicon, and that gives this bond a very good stability. That's why it breaks. Fine. So similar way like NBS, as I told, discussed previously, first bromination on this C3 position followed by the removal of tips to get 3 bromo derivative. Even DMF POCl3 DCM, this is a Vilsmeier-Hack reaction. So similarly, after this step means quaternary ammonium fluoride, we get this. So a question comes, can we consider this thing as a protection deprotection chemistry? Obviously yes. Why? Because first of all, we are providing protection, better to say steric protection of C2 position. We are doing some chemical reaction after this protection, and after completion of our reaction we are deprotecting. That's why we can definitely consider this thing as a protection deprotection chemistry. Okay, I believe this is a pretty interesting, because from direct AES on this 5-member heterocyclic compound, you will get C2 substitution. By this technique, you will get C3 substitution. So I suggest you please try to understand the logic properly, such that in which case whatever you need, you can prepare through proper choice of reagent. Okay, fine. Now let's go to discuss some specific example. This is the last part of this discussion. Now if you take the 2-acyl derivative, if I ask you how can you prepare this, I think you should answer acetic anhydride and pyridine. Sorry, acetic anhydride and pidol. Okay, fine. If you take this, and this is considered the alpha substitution, and if you react this in presence of trifluoroacetic acid, it converted into the corresponding this beta or C3 substituted product, and after 78 hours, what is observed that the amount of beta is 81%. This is more compared to the alpha. Question 5. So in order to understand that, first you need to understand the acidity of trifluoroacetic acid. See, trifluoroacetic acid pK is 0.23, whereas simple acetic acid pK 4.74 or 75, like that. So from this, what we can conclude, this TFA is a strong acid. And why strong acid? Because of the presence of 3 fluoride atom which are highly electronegative in nature. That's why this CF3 is withdrawing, and that's why the acidity is higher. Fine. And the temperature is also pretty high. And actually one of the another interesting point, you may consider that this is actually KCP, means C2 is actually KCP, kinetically controlled, because the corresponding energy of activation for the preparation of C2 is less, because the intermediate sigma complex is stabilized more because of 3 canonical forms, whereas in case of C3 this thing has 2 canonical forms. So this is actually a TCP or thermodynamic control product. This is my personal opinion. You may consider the story like that. Okay, so how the reaction occurs? Actually the reaction occurs in the first stage, AES occurs, and what it results? It results in AES using proton, because as I told, this is a relatively stronger acid, so it will generate proton, and C2 substitution occurs. This, so C2 proton attachment at the C2 position. Okay, by the way, positive charge is here, which is resonance stabilized. I have discussed this thing previously. Now you may think, sir, why not this? There is a reason, I'll come. So after that, in next step, 2 options possible. The proton, means this proton could be eliminated, one option, then we'll get back the starting material. Another thing possible, that this group can migrate with its bond pair. Okay, so if it happens, then what will result? This, it will directly convert it into this TCP. Now the question is, why not the reverse one? See, in this case, AES happening on C2. So AES on C2, but in this case, if it come to revert back, then AES need to happen on C3. Means, what do I mean? Positive, sorry, there is proton, there is COCH3, and sorry, there should not be any, and there should not be any. So there will be positive charge here. Now after that, it need to be migrated to go back to the alpha one, but this is actually a C3 substitution type, so it is associated with higher energy of activation. So if something is associated with higher energy of activation, means the back reaction, you have provided this higher reaction temperature, then what we can expect? That after a significant amount of large time, this 7 hour, the population of this TCP will increase, and which is reflected by the ratio. This beta 1 is 81%. Fine. So that is the explanation for this observation. Please remember, a MCQ could be constructed that after this, what is the structure of the product? Very simple, but if you don't understand the chemistry, you may feel difficulty. By the way, a similar example, this conversion, means in case of naphthalene, you will find the alpha substitution is associated with lesser energy of activation, but if you keep this thing in for a long time and higher temperature, what happens? This alpha converted into the beta. This is a very common in naphthalene. We will discuss, but as a comparison, if you remember this example, it will be helpful for you to remember both, because one example is actually helping to remember other one, because they belongs to the same logic. Okay, fine. So this is the explanation of the example number 1. Now let's discuss the second example. First of all, lots of chemistry in this example we will learn. So see, just look at the reaction medium. It is very important. Aqueous NaOH 100 degrees centigrade. So and you are providing carboxylic acid. So what will happen? First of all, it will undergo decarboxylation, means it will undergo deprotonation, means carboxylic acid will be converted into corresponding salt. Point number 1, fine. Now see, carboxylic acid is highly electron withdrawing, but its carboxylate anion is not that much withdrawing. Point number 1, because this negative charge. Fine. And iodine actually here the electrophile. Now question, why I am using Ki? What is the role of Ki? Actually the role of Ki is for, because this Ki and iodine react, and what they generate? Ki3. This is nothing but polyhalide anion. Question, why I need this? Just look at the reaction condition again. See, reaction is carried out in aqueous NaOH. No organic solvent is there, and iodine is not that much soluble in aqueous solvents. But if you put Ki, it forms converted into ionic salt, so it is soluble. So in order to bring the iodine molecule into the solution, Ki is added. Okay, that is the purpose. Now we know that iodine is electrophile. So what we can expect? That aromatic electrophilic substitution will occur, and which position? Generally C2 prefers. So one C2 is this, one C2 is this, but the reaction will happen on this. Why? I will explain. So first of all, it will produce, this is iodine, this is this O minus, positive charge is here, C2 substitution. Now in next step what will happen? These carboxylate will undergo decarboxylation. Okay, and in this way aromaticity will gain back. So this is, but this type of facility is not possible for this side C2 attack, this side, the opposite C2 attack, not possible. That's why, second, always remember that decarboxylation is highly favored. Why? Because carbon dioxide molecule is a very stable, and it, so enthalpy of reaction is higher. Second, it is a gas, so another molecule produced, so entropically it is also favorable. And another thing, it goes out from the reaction medium, so equilibrium is also preferred in the right hand side. By the way, if you feel any difficulty in understanding, just try to remember the aromatic electrophilic substitution on simple benzene or this pyrrole derivative, where at the last stage proton is abstracted in order to gain back aromaticity. In this case mechanism is similar, but instead of proton, this carboxylic acid is eliminated. So that is the difference. Okay, so a lot of chemistry we have learned in this video. So in conclusion, what we have learned today? In conclusion, we have learned today about that aromatic electrophilic substitution on pi excess nucleus occurs easily, and the activity orders generally, pyrrole is higher than furan, than thiophene, than benzene. Exception, you may find some exceptional case, but this is general. Fine. And this application of relatively drastic condition for AES on such kind of this heterocyclic nucleus may result in polysubstitution. Okay, so that's, we don't expect, we want selectivity. Finally, generally it is easier to introduce electron deficient substituents through AES on this 5-member heterocyclic nucleus, but electron rich, it is difficult because they are already active, and if you put further activating group, it will be very difficult to control the reaction and maintain the selectivity. Fine. And most importantly, for furan, it is possible to do base controlled reactivity, because in furan base can abstract the NH proton, and which will further increase the reactivity. I shall upload a dedicated video, don't worry. So, and this is possible for pyrrole due to presence of that NH bond. Okay, fine. So this is the end of this discussion. I believe this video may be useful for you. Thank you all for watching this video. And if you really like my teaching, I request you please like the video, make some good comments, or write your opinion on the comment box, so that I can understand what's my positive, what's my negative. about my teaching. And most importantly, if you think this video is worthy, then share with your friends such that they can also enjoy the benefit. And most importantly, if you find my work is deserving, then please subscribe this channel and please press the bell icon such that you get notification of every new single video I upload. Till now, stay happy, stay blessed, and I want to end this lecture with the optimistic point. Don't lose your hope. Continue work. One day you will definitely be successful. All the best, all good wishes from my side. Take care. See you in my next video.